you probably know that I'm addicted to Lagrangian mechanics problems. So I have this problem. It's called, I think it's called Kapitza's pendulum. It's an inverted pendulum with an oscillating pivot point. So this pivot point can move up and down, and apparently this is stable in the vertical situation. So you can have the mass up here and it'll be stable. You can have the mass down here. There's a video of a guy that made this with a jigsaw. I'm going to show you that video. So let's switch over to the video. Okay, so here is the video of the jigsaw. So you'll notice that when he puts the stick in the vertical case, so this has the jigsaw moving up and down, the pivot points attached to the bottom of that, and you can see it's stable. I'll put a link to this video down below. Okay, so yes, we're going to do this in Python. Okay, so this is the Lagrangian mechanics problem, so let's just get right to it. We define Lagrangian as the kinetic energy minus the potential, and there's only 1 degree of freedom here. Yes, this moves up and down, but since this is a fixed distance, I can describe the whole system just by some angle from the vertical, which I call theta. And if that's the case, once I find the Lagrangian in terms of theta, kinetic energy minus potential energy, then the Euler-Lagrange equation will give me the equation of motion. So it says the partial of L with respect to theta minus the time derivative of the partial of L with respect to theta dot 0, and theta dot is just the derivative of theta with respect to time. We write it like that just to make things look better. You could probably use intuition to write down the kinetic energy in this case, but I don't want to do that. I mean, I think it's dangerous to kind of like just use your intuition. So instead, we can write the kinetic energy as 1/2 m x dot squared plus y dot squared. I know that that is one way to write the kinetic energy. So if I can get x and y in terms of theta, then I can use this expression to convert the whole thing into theta dots. So let's say this is the origin right here, and this moves up and down with the position of a sine omega t. Then what's the x value up here? Well, in that case, I could just say x is going to be equal to this distance r times sine of theta, right? It doesn't depend on how that thing moves up and down. That angle's still going to be theta, then the distance this way is going to be r sine theta. That's it. Now for the y direction, I have to take, it's going to be r cosine theta is this distance, but that pivot point moves up and down. So I'm going to say plus a sine omega t. So that's my thing. Now, this is not hard, right? I can take the derivatives, square them, and add them together, and it's not too terribly difficult. But since I don't really want to go through the mechanics of the algebra, I'm going to use, I want to practice, I'm going to use SymPy, Python SymPy in Google Colab. And it's a good idea to practice that just because if I don't, I'll forget how to do it. So let's jump over to the computer, and I'll show you how to do this. I've done this a couple of times before. Switching right here. Okay, so I didn't switch to the computer. So I already have, this is Google Colab. So you can actually do your Python code in Colab, and you can do it all online. You don't have to install anything, and I think that's awesome. So the first thing we need to do is to import the Python module that we're going to use, SymPy. So I'm going to say import SymPy as SP. And I'm going to run that cell. I like to run that cell just to make sure everything's working beforehand. Okay, so now I need to declare my variables. So what variables am I going to have? I'm going to have time. I'm going to have r, m, g, omega. Is that it? I might have another one. And that's going to be, I need to tell SymPy that those are going to be variables. And here I'm calling omega w. You could call it, you could write out omega. It would actually look better, but I don't want it to look good. I want it to use good. So I'm going to write it that way. So I'm going to call this sp.symbols. And then I need to retype what they are. T, R. You don't have to put commas here, which is really strange for me. W. And I think that's it. Oh, A. I need A. And so I'm going to put the A there too. I didn't put my parentheses. A, parentheses, and that's that. Okay, now I have another variable, theta. Theta is a little bit different, so let's call that one different. I'm going to say theta is sp.symbols. theta. And it's going to be a function of another variable. So I'm going to say its class is sp.function, capitalize, and that's that. Now I'm going to say theta equals theta as a function of t. And just so you can know, I can run that. I'll print theta. Let's just run that so you can see how it works. So you see it wrote it as theta as a function of t, which is really useful. So it knows that I know that it knows. We're all cool. Okay, now I need to know theta dot and theta double dot. So I need the derivative of theta with respect to time and the second derivative. So I'm going to say theta dot, I'm going to make that name, is going to be equal to the derivative fp dot diff is differentials theta with respect to t. And then theta double dot is sp dot diff theta dot t. Right? Okay, now what do I need to do? I need to define my x and y variables. So I'm going to say, just like I said before, x equals r times sine, sp dot sine theta. So sine's not built into Python, so I'm using sine from SymPy. Y equals a times sp dot sine omega times t plus r times sp dot cosine theta. Just like I said, it's the same thing I wrote on the paper. Nothing new there, right? I'm not trying to trick you or anything. Now I can write down the kinetic energy. So T is 1/2. So in SymPy, if I want 1/2 to be a fraction, I have to say sp dot rational 1/2, 1/2. Okay, then it's going to leave it as a fraction. You could put 0.5 and it'd probably all work, but I think it's a good idea to get in the habit of doing it this way. Times the mass, m, times x dot squared, sp dot diff xt squared, plus sp dot diff yt squared. And so SymPy does all that algebra for me. And it's not bad algebra. You can do it on paper. It's really not too bad. If you want to see what that looks like, I could say t dot simplify and then run that. You can see that's my kinetic energy term. And so you see it has theta, theta dot squared, t, omega, theta, theta dot squared, all that stuff. Now I need the potential energy, which is pretty easy. It's just going to be m times g times y. L is going to be equal to t minus u, and that's that. If you want to write out, if you want to see the Lagrangian, you can, but you know, nothing surprising there. Okay, so next thing I'm going to do is to write the Euler-Lagrange equation. So I'm going to call that LE, and it's going to be equal to the partial of L with respect to theta, which is sp dot diff L theta, minus the derivative sp dot diff of sp dot diff L theta dot t. That's my Euler-Lagrange equation. Right, so I'm going to take the derivative, subtract the time derivative of the partial of L with respect to theta dot, and that's that. Now I need to solve that for theta double dot. So there's only one variable here, so it's not a really big deal, but I'm still going to do it this way. I'm going to say the solutions is sp dot solve. Now I need to list what equations I have. I only have one, LE, and then I want to know what variable to solve for, theta double dot. And now that's going to give me a list, but let's just print it out, sols. And there's a problem. The problem is I can't spell, right? It's not solvel, it's solve. So there's my solution right there. That's the solution for theta double dot. Now you'll notice it's a list. You see the square brackets with one element in there. So I could just print out the first element like that. And there you go. Okay. So now what I want to do is to get that. And you'll notice that's W, not omega, because I told it W. Here's a trick. I want to write this and move this to GlowScript Web v Python, so I need that function so I can model the whole thing with a numerical calculation. So to do that, I'm going to do this. I'm going to say, let's say f theta double dot, that's going to be my function for theta dot, is the string of sols 0. And then let's just print that, just so you can see what it looks like. Oop, what happened? I'm going to turn it into a string. So now I'm going to say print f theta double dot. And let's just see what it does. And so it print out the not the nice math equation version of it, but the symbol. But you see here, I couldn't use this in WebP Python because it has theta t, right? Theta is a function of t, but when I use it as a numerical calculation, I just want theta. Everything else looks okay. Everything else is exactly the way I want it. So I'm going to replace the theta t, and you could easily just do this manually, but I'm not gonna. I'm gonna say f theta double dot equals f theta double dot replace. I want to replace. I'm going to do a string operation, which I don't normally do string stuff because I'm not a string guy. I'm going to replace theta t with theta. Oh, got to put in print quote theta. And then I'm going to print that. Print f theta double dot. And so then it took that theta t and replaced with theta. So this is what I want, right? Now I can just copy this. I'm going to copy that. Now I can go to GlowScript vPython and model the whole thing. And again, I could have just typed this out easily, but I'm trying to get in good habits. Before I was copying and pasting this in a text editor and doing this manually, but this is a little bit more Pythonish. And yeah, you could model this in Colab, but it doesn't have the visual module in here, so I can't do that. Okay, so here I am in Trinket. Let's just put this as a comment before I forget. The first thing I wanted to do is declare my variables. So I'm going to say g equals 9.8. The mass, let's say it's 0.1. R, I'm just trying to think in my head, it's half a meter, 0.5. A, how high up and down does that thing move? Let's say it's a centimeter, 0.01. Oops, I got to put equals. 0.01. Omega, let's say that's 50 radians per second. We can change that. Now I need my, is this big enough? Now I need my, ooh, that's too big. Ooh, what happened there? Now I need my initial condition. So t is 0, dt is 0.001. I'm going to make dt small because if I'm going to have that thing oscillating really fast, it's going to matter. Theta is, let's put it tilted to the side. Yeah, let's say 0.1. And then theta dot is 0. So the initial angular velocity is 0, and that's that. Okay, so now I need to start drawing some things. The first thing I'm going to do is put my little oscillating node. Let's call it a node. I don't know if that's what it's called. So node is a sphere. The position is going to be equal to a times vector 0 sine omega times t 0. Right? So that is just going to start at 0, but 0, 0, 0, but that's what I want. How big is it? Let's see, radius equals, let's say 0.005. And let's do make trail equals true, just so we can see it. I'm just going to run that. Okay, so it zoomed in on it. Nothing's really great. I guess I should save this. Kapitza pendulum. Oops, pendulum. And I'm going to give you the code. Okay. Now I need to make the other mass. So let's call it mass. It's a sphere. And I'm going to say its position is equal to, let's do this. X equals r times sine of theta. Y equals a times sine omega times t plus r times cosine theta. All right, so I'm calculating x and y. So down here I can just say the position is vector x, y, 0. So then, and I'm going to use that same expression later, so it's good. Now, what about the size of this one? Let's give it the same radius. 0.005. Let's make it yellow. Color equals color. Dot yellow. And make trail, I like the trails. Make trail equals true. Okay. Now I do want to make a rod connecting those two things. So I can say rod equals cylinder. The cylinder object in Python has three important properties. One is the position, which is if I have this is a cylinder, the vector position of one end, and then I need the vector from here to the other end, and then the radius. So I'm going to say POS equals node.POS. So node.POS is the location of node. And then the axis is going to be equal to mass.POS minus node.POS. That's the vector from the beginning to the end. And then radius is 0.002. I don't know, make it skinnier, I guess. Okay, let's run this and see if that works. Just see what it looks like. Okay. Maybe I should make the things a little bit bigger. So let's make this 0.1 and this 0.1 and this 0.5. Let's just try it. That didn't work. That's small. What does that do there? Aha. Okay. Okay, that looks good enough. Okay, we are ready to rock and roll while t is less than 5. So I'm going to run it for 5 seconds. It doesn't really matter. Rate 1,000. So this says don't do more than 1,000 calculations per second. So with that time rate, this will make it run in real time. The first thing I'm going to do is to calculate theta double dot. So I already did that. It's up here. Copy that. Down here, I'm going to say theta dd dot, that's what I call theta double dot, is that. That's it. Now, once I know theta double dot, I can use that during this time interval to find theta dot at the end of the time interval. So I can say theta dot equals theta dot plus theta double dot, theta double dot times dt. Now I can update theta. Theta equals theta plus theta dot times dt. So now that's it. I need to update the pictures of everything. So let's recalculate x and y. Right there. And then I need to, let's move the node. So the node is actually going to be the same thing. Node.POS is going to be the exact same thing it was before. The exact same calculation. But now t changes. So it is going to move. Then the mass.POS is going to be equal to vector xy0. And the rod, I do need to move its position since the node moved. Rod.POS equals node.POS. Rod.axis equals mass.POS minus node.POS. And then I need to update time, t plus dt. Will this work? I don't know. Let's see. Okay. It fell over. It looks cool though. Okay, so it's not. Is it working? I don't know. I think maybe my frequency has to be higher. So let's go up here and just change this to 200. Oh, it's getting better. Let's try 300. And now I'm getting scared. I'm going to make the time step even smaller. I want to make sure that I have plenty of calculations. Let's make it 500. There it goes. That's really interesting. You know, and I wonder at what point do you have to get it to be stable? How fast of a frequency? Let's just try 400. That's not 400. What the heck? That looks stable. What did that change? 500? See how fast that's moving right down there? And that changed up to 400 and it just doesn't look like it's very fast. I think there's a sync problem. Let's try 440. Let's just see what happens there. Yeah. Okay, let's try 340. Oh, it came back. Okay, let's try 310. Okay, there. So that wasn't enough. Now, I wonder about if I increase the amplitude, will that make it stable? I'm just playing around here. And I'm assuming that things are correct here. So double the amplitude of the node part. Oh, that helped. Okay. So I think you could, I would love to take this and explore the when is it stable, plot the stability as a function of time, as a function of both the driving frequency and the driving amplitude, and then even try building this. You could really build this, right? You could even change this so it's a rod instead of a mass at the end. But there's all sorts of fun things you could do exploring this. Hopefully I'll get someone else obsessed with it. You know who you are, and we'll just see if he even makes it to the end of this video and does it. But if he does, it'll be super quick. I know him. It's going to be quite quick. He'll probably build something cool. So that's the Kapitza's Pendulum. Kind of a fun Lagrangian problem, and not really a difficult one either. You don't even need SymPy to solve this. It's not too complicated. So I will give you the link to this code. I'll put a link to the Kapitza's video down below, and I hope you have fun.